don't always I don't always record everything, but I'll record this. And it is just a description of the way to solve number 4. Maybe number 4 was the most challenging. I don't know why, but um, a lot of steps to it, I guess. If you wanted to, you could just take this formula for cost, plug it into there, take this formula for price, plug it into there, and you have pi equals q, like this right here. You have pi equals something that only involves q. Just take the derivative of that function, pi prime if you want, with respect to q, and you get this simplified thing. You set that equal to 0, and you get the answer 22.5. How do you know the answer is 22.5? Well, I guess you could check the corners. The corners are 0 and 100 here. This is the choice set. Q has to be chosen between 0 and 100. So you could check the corners 0 and 100, but really quickly, you can tell this firm is going to make no revenue at all if P equals 0, or sorry, if Q equals 0, and they'll make no revenue at all if Q equals 100 because 10 minus 100 over 10 is 0. So you can eliminate those corner solutions really quickly. And the answer is 22.5. I think it's good to remind us all that we're doing economics now, not just math. And the economic intuition behind this problem is correct. You don't have to choose one or the other. They're actually both true. And the economic intuition about a problem like this, how to solve for profit maximization in this case, would be, we'll set marginal revenue equal to marginal cost. And if you remember how to find marginal revenue, you can actually take a demand curve like this, P of Q, and just double the slope of the demand curve. So here the slope is 1 over 10. If you double it, it's 1 over 5. And set that equal to the marginal cost. 10 minus Q over 5. I'm sorry, set that equal to the marginal revenue, 10 minus Q over 5. What's the marginal cost? We just take the derivative of the cost function. That goes away, it becomes 1 plus Q over 5. So it's 10 minus Q over 5 equals 1 plus Q over 5. Subtract 1 from both sides, you get 9 equals, and then you have 2 Q over 5. So multiply both sides by 5 halves, and you get 45 over 2. That's the answer. I guess my point is treating this as just a function. Pi is a function of Q. Use the first order conditions, and then verify the second order conditions, and then arrive with the answer. That's sort of the way I'm just teaching you how to do it in this class. However, if you remembered the way from micro, how to solve a problem like this where marginal revenue equals marginal cost, you could have got the right answer there too. And I like it when you give those sorts of answers to you. Either way, you're going to get 22.5 as your answer. Okay. What else should we do today before we do the quiz? Let's do the quiz at the end. That way you have, people take different time to do the quiz, and doing it at the end has the benefit of you can just leave the class after it's done. So can we talk about some matrices? You remember last week, that's what we were doing? Do you remember how to multiply matrices? It's not just term by term. You don't just take the top left term, multiply it by the top left term of the two matrices, and that's how you get it. That's correct for subtraction and addition. It's not correct for multiplication. For multiplication, you should remember there's this row of the first matrix times column of the second matrix procedure that you do for every entry that you're trying to define in the product matrix. Let's review that a little bit. Last time we did a 3 by 3, and that took a long time, but let's just review some 2 by 2 matrices. I gotta share that with you. It is right here, the thing I would like to share. I can't press the slideshow button because it's in the way. Okay, matrix multiplication. This is once again the description of it that I gave you last class. here's again a reminder that you can only multiply when these ends match up. You know, the second dimension of the first matrix has to equal the first dimension of the second matrix. Then it's possible to do the multiplication. Otherwise, it's not possible to do the multiplication. We did that last time. We talked about the transpose last time, and some examples of what it means to be a transpose will be useful here. Just it's pretty straightforward what it means. But you flip the rows and the columns. The first row becomes the first column. The second row becomes the second column, etc. So unless you have any questions, I'm gonna go on. Here's an example of matrices that we can. I'm testing you right now, not for points, but just to see if you know how to do this. What is A times B? I would like you to do that yourself. Tell me what you can see. Matrix A is up here. It's the matrix 1, 2, 3, 4. B is this matrix 2, 0, negative 1, negative 4. The question is, what is A times B? I'll do it also. And if you've forgotten how to do it, let me remind you. The first thing you should do is take that the first row of A and multiply it term by term with the first column of B, right? So you can see that 1, 2, and a 2, negative 1, you should multiply 1 times 2, and you should multiply 2 times negative 1 and add those together, right? That would be the upper left term of your answer, of the answer A times B. And then do that for the other ones too. Upper right, what would you get? Well, now you still have that first row of A, 1 and 2, but now you have the second column of B, which is 0, negative 4. So 1 times 0, 2 times negative 4. Add those together. That's your answer for the upper right number. Then do it for the bottom left number, do it for the bottom right number, and then you're done. If you want to go on and do these other ones, like B times A transpose times B, A transpose times A, you can go ahead. I can't make you do anything since we're not even in the same room right now, but I do strongly encourage, at least so you get through this, what is the process of matrix multiplication? At least do A times B. Make sure you got that. If you want, I can then trust that you could have answered the other ones if you wanted. Light, give myself a little more light. And I'm lit from the side. Has anybody got A times B yet? Or is anyone still working on A times B? Maybe I should say it that way. Where's the chat? I don't see any chats. I'm going to start chatting. Hello, everyone. Anyone got? Should I say anyone got or anyone hasn't got? I'll say anyone got. Anyone got AB? The answer for AB?
I got it, I think.
Okay. Are there some people still doing it who want more time? If not, I'm going to ask Kai to give us her answer. Nobody's chatting anything. Okay. Why don't you tell us what you got, Kai?
I got 0, negative 8 to negative 16.
Sounds good. 0, negative 8 to negative 16. You guys all see how she got that? It's this, what I have here is like the 1 times the 2 is 2. The 2 times the negative 1 is that negative 2, right? So this is a little bit of a breakdown of how you get A times B. So you can just see, here's the matrix A, here's the matrix B. It means something for those two matrices to be multiplied to each other in a sort of non-trivial way. What I mean is that it's really not a straightforward thing to do to look at A and look at B and have some idea of what A times B will be. There's all this arithmetic that's going on. Like if I gave you just two numbers, like what's 3 times 4, you could picture that easily. You'd say, oh, it's 12. And you could even picture it as like 3 rows and 4 columns and a little rectangle, and how many dots are in that rectangle? 12. I'm just saying for matrices, it's a bit harder to visualize multiplication. And that's because the actual information that's embedded in a matrix is a little more complicated than we realize, at least at first look. There's something called a determinant of a matrix that is a good way to sort of capture what's really going on in a matrix. What's really going on with this matrix A? Well, the determinant says something important about what's going on. So I haven't told you yet what the determinant is. Maybe you already know, but in just a little bit, we'll talk about what the determinant is and how that actually you can multiply, right? So if you have the determinant of A, the determinant of B, then you know that the determinant of A times B is equal to the determinant of A times the determinant of B. So that's what gets preserved in a matrix when you do this multiplication, is the determinants, but not the numbers themselves. Like, why is this upper right one negative? I mean, I don't know. There's a lot of positive numbers here, but it just happens to be negative. Okay. Like I said, you didn't have to do B times A or A transpose times B. Will someone just tell me what is A transpose in this case? Just give me the matrix. Read it out from left to right. What is A transpose?
1, 3, 2, 4.
Thanks, Colin. He's correct. Everyone see, the only thing that changed were the 2 and the 3. They flipped. He's correct. Let's look at the answers. I'll show you the answers for if you're still working on BA or AT times B or AT times A. That's okay. I'm sure you got far enough, and I applaud your efforts for attempting to solve those. So here's B times A. And notice it's different. It's different than A times B. Here's AB, here's BA. These are two different matrices, so it matters which order you do the multiplication. However, the determinant of these two matrices has to be the same. I know that. I know that in some sense, this matrix A times B and this matrix B times A, they have something in common, which is that they have the same determinant. We'll talk more about that later. What's A transpose times B? I got this. -1, -12, 0, -16. Unless I made any arithmetic errors, I hope that's correct. Maybe that confirms with what you got. And then finally, A transpose times A. 1, 3, 2, 4 times 1, 2, 3. 1, 3, 2, 4 times 1, 2, 3, 4 equals this. And I wrote a little note here that says A transpose A is always symmetric. You could easily convince yourself of that, because what does it mean to be symmetric? It means you're equal to your own transpose. So if you take the transpose of A transpose A, you would actually get A transpose A. It's this. Let me go back to. I think I wrote this right here. This final thing. AB transpose equals B transpose A transpose. So if you're taking the transpose of A transpose A, then what you're going to do is take the transpose of both matrices and reverse the order in which they're multiplied. That's exactly what's happening here. If you take the transpose of both of these and reverse the order in which they're multiplied, you get itself, right? A transpose becomes A becomes A transpose. You reverse the order, and you get right back A transpose A. So that's a nice property, that any matrix times its own transpose is symmetric. Why should you care about that? There's some nice properties of symmetric matrices that we'll talk about in this class. In particular, the higher the more complicated derivatives of functions, I'm just gonna go talk about the future here. We're gonna talk about functions of more than one variable. So this is a function of x and y and z, maybe 3 variables, x, y, and z. If you want to talk about the derivative of this function, you have to specify with respect to which variable, x or y or z. So if you start talking about more complicated derivatives, maybe I first take the derivative with respect to x and then y, or I take the derivative with respect to x and then z, or z and then y. All these different combinations, it can be pretty complicated, and it makes sense to organize all of that into a matrix. This is part of the reason I'm teaching you matrices now, so that you'll be more familiar with them later. If all of these derivatives are just packed together in a matrix, if that matrix is symmetric, then it makes it easier to do operations, to prove things about it. You know, let's say your real goal is to prove something nice about this function and its derivatives, and you get this matrix of derivatives. If the matrix is symmetric, it's easier to prove something about that matrix. And so this notion of transpose and symmetry, it's nice to have later, even though right now I'm not giving you very good intuitions for why it matters. You guys have any questions about, so you should be comfortable with multiplication and transpose. Good? All right. Next thing I want to talk about is, go to the next slide. Inverse. Inverse is very important. You notice I haven't said anything about division of matrices. Just because you can't divide by a matrix. It doesn't make sense to say matrix A divided by matrix B. However, there is something known as an inverse, which is, it's sort of like division in the sense that it has this property where if you have a matrix A and you multiply it by A inverse, when you see this -1 sign, this is another kind of cue signal to us that it's kind of like division, because if you think of something raised to the -1 power, it's kind of like 1 over that thing. It sort of means that, but it doesn't literally mean that. It's just a symbol. So if a matrix, by the way, I'm going to minimize everyone up here, so if you're watching, you won't see all the people. If you take a matrix and look at its inverse, you can only do that if it's square. Only a square matrix, that is the dimensions of the row equals the dimensions of the column. That's the only matrix that could possibly have an inverse. If it does have one, you call it a -1, superscript -1. You just read that as A inverse. It looks like A to the -1 power, but don't call it that. Just call it A inverse. And it has this property where A times A inverse equals I, where I is the identity matrix. The identity matrix, you can kind of think of that as 1, even though it's not a matrix filled with 1s. It's a matrix with 1 on the diagonal and 0s everywhere else. Okay, so instead of division, we can think of the inverse of a matrix as the quote reciprocal unquote. In this case, the quotation marks indicate that it's very, very nearly correct to call it the reciprocal, even if it's not quite. And in some cases, multiplying the inverse of the matrix is equivalent to dividing. Warning, the order of multiplication still matters, right? So if you want to, if you want to divide by a matrix, you could say, okay, I'll just multiply by the inverse. That's like dividing. Well, yes and no. It still matters whether you're pre-multiplying or post-multiplying. And therefore, even this concept of division isn't very consistent when you're talking about matrices. Okay, here's more definition. If a matrix does have an inverse, what should we call it? We could either call it invertible, meaning that you can invert it, or you could call it non-singular. And this sounds like, where's that coming from? Singular just is by definition a matrix that cannot be inverted. So non-singular means that it can. Here's some properties. The inverse of A inverse is A, of course. How about this? A times B inverse is equal to, just like transpose, you take the inverse of both matrices and then reverse the order. The same thing is happening with transpose. So I think that's kind of neat there. AB inverse equals B inverse A inverse. What about transposing and inverting? Actually, those are commutable. You could do those in either order and it doesn't change. Here's a warning. There's no way to simplify A plus B inverse. Don't try to do it. If you get A plus B inverse, the only thing you can do is actually calculate what A and B are and then take the inverse of it. There's no simplification there. Okay. So inverse, we need to learn more about inverses. Oh, but before we actually by the way, there is a way to calculate inverses, but I'm not going to ask you to do it. The reason is it would just take too long and I don't think it's worth it. You can look it up in a book, how to find the inverse of a matrix. Another thing you can do is use a calculator or an online matrix tool. There are online matrix tools where you can plug in a matrix. It'll tell you the determinant of the matrix. It'll tell you the inverse. It'll tell you whatever you want. So I'm not going to actually have you learn how to find the inverse, but you do need to know what an inverse is. Okay.
So does that mean, like, for quizzes, are you going to be looking for our work so that you know that we know how to do it, or are you just looking for the answer?
Are you talking about for an inverse?
Or just like any matrix multiplication, I suppose, or like that?
Good
like
question.
That, or even determinant. I know you can.
Yeah. So if I ask you to do some kind of matrix multiplication, I actually do want you to show me the work for that. Okay. For that one, yes, please.
Cool.
But for something like, okay, yeah, good question. For something, how about this? Unless I say, you don't have to show your work unless I say for matrix operations, because I know that there's software out there that will do it quickly. And, if you want to be crystal clear, you can say, oh, I used this calculator to get the answer. Then I know how you did it. I want to know how you did it, just so I don't think somebody handed you the answers and you copied them down. It's nice to see that you actually did it. And if I want you to actually go through the arithmetic, I'll ask you to. Okay. Good question. But for inverses, I'm not asking. I will never ask you to calculate inverses yourself. It's too hard. And not that you couldn't do it. I don't feel like making you do it. Let's talk about the determinant now. Good question, Colin, but let's talk about the determinant. Make sure we leave myself enough time for the quiz. It is 1 o'clock now. Class goes to 1:45. I really only want to go for 10, 15 more minutes and then we'll be done. So what is the determinant of a matrix? It is just a useful number. That's it. A useful number that captures something about a matrix. And if you have a matrix here where A, B, and C, D are any number, how do you calculate the determinant? It's this diagonal A times D minus the other diagonal, B times C. That's what the determinant is. You need to know why it's A times D minus B times C. I don't think that's particularly important, but that's what a determinant is for a 2x2 matrix. Well, what about for a larger matrix, 3x3? You can't use this formula AD minus BC because it'll get bigger and bigger, but you can reduce it. So for example, a 3x3 matrix, how do you find the determinant? You can reduce this big 3x3 matrix as, you can pick any row, let's just say the first row. So let me talk now about how to find the determinant of a 3x3 matrix where the elements are A, B, C, D, E, F, G, H, I. Those are the entries of the matrix. I can pick this first row and say, I'm going to take the determinant of this submatrix, which is obtained by eliminating the rows and columns of A. I can find the determinant of the submatrix obtained by eliminating the rows and columns of B and the submatrix for the rows of columns of C, and multiply those determinants with the numbers A, B, and C with alternating signs. So it's positive A, negative B, positive C, and that will be the determinant of the whole thing. So that's what I've written out here in terms of letters. I know that was a lot. I'm sorry. I'll probably post this on YouTube if you want to go back and listen to exactly what I said. But I think you'll make sense of this just by doing it once or twice. But let me go through it again. Oh, go ahead. Say it again.
Is this kind of where you draw the lines, and like wherever the intersection of the lines is the letter that goes outside of the parentheses? Like I wish I could draw, but like if
is that how you learned it in another class?
Yeah, it was just a little bit easier because we would put like for the first one A, you would put like a vertical line on the first column, and a vertical line on the horizontal.
Yes. Yeah. So take the number A, draw a line through the row and the column, and what's left is EFHI. And then you use this formula up here for how to do the determinant for a 2 by 2. You already know that. It's AD minus BC. So here it's EI minus FH. So you take the A, that's the first row, the first column, and like Colin said, you can like cross out the row, cross out the column, and what you're left with is this EFHI. That's where this EI minus FH comes in. Hopefully you can see my cursor because I'm using it right now to highlight which part of the equation I want you to pay attention to. So it's A times the determinant of this EFHI, which is EI minus FH. That's the whole first part. The second part is, well, the rule is you have to keep doing it for one entire row. Doesn't matter which row you do it, but if you're doing it for the top row, you start with A, then you have to alternate sign with this B. So there's a negative sign right here, minus B times what? DI minus FG. That's the determinant you get if, like Colin said, you drew a line through this column and a line through this row, you'd be left with the matrix DFGI. And the determinant of that, you can use this formula up here, or just think about it like diagonal DI minus FG. That's where this comes from, DI minus FG. And then the last term, we alternate in sign again. It was positive A minus B, positive C. Cross out this row, cross out this column. You're left with the matrix DEGH. And to take the determinant of that, you get D times H minus E times G. That's what this is. So this formula here, and of course, I don't know if it's of course, but I'll tell you now, I'll never have you calculate the determinant, at least by hand, of any matrix that's bigger than 3 by 3, right? You could do this for a 4 by 4 matrix. Well, I'm hesitant to even explain to you how to do it for a 4 by 4 matrix, but it's the same process where you can reduce a 4 by 4 matrix to a bunch of 3 by 3 determinants. And you reduce the 3 by 3 determinants to a bunch of 2 by 2. You can still do that, but it's very time consuming. I'm not going to ask you to do that. But I do want you to know what a determinant is and how you could calculate it for a 3 by 3 matrix. And remember, what is the determinant? It's just a number. It takes a big thing like a matrix and condenses it into one number. And the number matters for various reasons. You guys have any questions about a determinant? You want to try it for some? I think in the next slide I have you try some determinants. Oh no, first I give you properties, and then I'll have you find one. Okay. Yes. Here's some properties of the determinants. What do I have? Oh my gosh, not that much time. If you had to try to visualize the determinant, I've seen this written before. I don't think it's going to help anybody visualize the determinant, but it's in some sense the volume of the figure spanned by the columns or the rows of the matrix. If you thought of the rows of the matrix as a vector, and then thought about what kind of figure is spanned by all of these vectors, and you calculated its volume, that's kind of like what the determinant is, but it's not important. But this is for a square matrix A, the determinant of A is not equal to 0 if and only if A is invertible. So any matrix that's square, you can take the determinant of it and immediately know if it's possible to find an inverse of that matrix. So I wrote it one direction here, I wrote it the other direction here. Determinant A equals 0 if and only if A is not invertible. So it's kind of backwards. Determinant A not equal to 0 means it is invertible. Determinant A equal to 0 means it's not invertible. This is an important quality of the determinant, important property, I should say. Here's some other properties. Of course, the determinant of the identity matrix is 1. No matter how big the identity matrix of dimension n, it's still 1. The determinant of a transpose is the same as without the transpose. Here, the determinant of an inverse is equal to 1 over the determinant of the original matrix A. So it kind of has this, it preserves this property that you would expect in multiplication, that if you're taking the inverse, if that's sort of like 1 over A, well, it's not exactly equal to 1 over A, but the determinant is equal to 1 over the determinant of A. And I said this one already, you can sort of split up A, B, and find the determinant of A, determinant of B, and multiply them. Okay, here's an interesting one. If you take the determinant of a constant times a matrix, so for scalar multiplication of a matrix, you don't have to do this whole add up the rows and columns term by term. You can just multiply every term in A by C. That's what it means to do matrix. I'm sorry, that's what it means to do scalar multiplication of a matrix. If you want to find the determinant of C times A, where C is a constant scalar, it's equal to C to the n power times determinant A, where n is the dimension of the matrix. By the way, you can only find the determinant for square matrix, right? This only works for squares. So that's why the n is unambiguous here. What's the dimension of the matrix? I don't have to say n by m or m by n. It's really just n by n matrix here. Okay. I'm wondering if we have time to find a determinant here. We probably don't. If you want to, look at finding this determinant for next class. But I'm gonna stop sharing here. We'll do this next class too. We'll find the determinant of this matrix. Okay, now I want to ask if you guys have any questions about the previous homework or the procedure of optimization with one choice variable, because I'll remind you again, this is the only thing I'm going to ask you about on this quiz. The quiz that I'm going to make available very shortly, it will just be like an optimization problem.
Yeah, I just had one question.
Okay.
So I know for the first order, we take the first derivative and then set it equal to 0 and solve for our parameter.
Correct. I wouldn't call it a parameter though. I would call it a choice variable.
Oh, choice variable. Okay.
Yeah. Parameter is generally something that you don't choose. Whereas a choice variable,
Oh, okay. Okay.
you do choose. Yeah.
Okay.
Go ahead.
And then for the second order, I know we take the second derivative, and if it's greater than 0, it's minimization problem. And then is that true, or is it? I always get that confused.
Yes.
Less than or equal to 0 is maximization.
So I have a little comment about the way you said it, because the if then of what you said it, I don't think is correct. I think actually it's if it's a maximization problem, then the second order condition is to set the second derivative less than 0. Max would go to less than 0. And remember, the difference between necessary and sufficient in this case is just whether or not there's an equal sign. It's necessary if you have less than or equal to 0, and it's sufficient if it's less than 0. Okay, and for the minimization, it's the opposite, where you should say, if you are doing a minimization problem, then the second order conditions are that the second derivative should be greater than 0. That's the sufficient one, and the necessary is greater than or equal to 0. Does that make sense?
Okay, so necessary has the equal sign, sufficient is the no equal sign.
That's correct.
or like less than or equal to. Slash. Okay.
Yeah. That sounds right.
All right. Thank you.